I know class hasn't started yet, but a quaternary amine is still called an amine. It's called an ammonium, even though it's attached to 4 carbons. Just looking. So a quaternized amine is an ammonium group. Whether it's got 4 carbons on it or 3 carbons and a hydrogen, it's still an ammonium. It is not incorrect to call it an amine. I'll accept amine. It's only kind of temporarily something else. So if it's got 4 carbons, it's technically an ammonium. If it has an H on it that makes it attached to 4 things and positively charged, it's technically an ammonium, but that's reversible back to an amine. So the reactivity of an amine that is not protonated, like, is neutral, and an amine that is positively charged is different. But yeah. So Jolene wants to round down to 5. We might, because I might get really bored. It will go live on Blackboard. I talked to the people at Top Hat and they said, we can't really do what you want to do. And I went, okay, I'll do it on Blackboard. So I'll figure out how to do it on Blackboard. You have it from, yes. So to be absolutely clear, it goes live Friday, 12:01 a.m. And it stays active until Saturday night, 11:59 p.m., at which point it will promptly kick you out. You have access to it for the entire 48 hours. It does not need to be completed in a single sitting. You will have access to 1 question at a time. You will not be able to go back. So if you don't answer a question, you can't go back and fix it. I will put all this in writing. And you have 48 hours to do it. There is no time limit. So are we not doing chapter 3? We're doing chapter 3, but we're doing chapter 3 later because 1, 2, 5, 6, 3. I've actually just updated the schedule here. You can see chapter 3 is down here. It's all, I've never figured out how to teach these 2. Because you can't really do chapter 3 without doing chapters 5 and 6, but 5 and 6 work better with chapter 3. So I'm been trying to do 5 and 6 first and going back to 3. I think it works better. I just disagree with how all textbooks do this. This is exactly what the schedule and the syllabus says. So I'm just matching this now to the syllabus. Can you leave the assignment and come back to it? Absolutely. You can leave the assignment and come back to it. Just do not hit submit. Because if you hit submit, then you've submitted it. We have not done chapter 3 yet. Chapter 3 is about confirmation. We have not talked about confirmations yet. We will be coming back to it. So if you've been following along using the syllabus and clicking the next videos, that's there. So today is Wednesday. And so we are discussing solubility and stability in functional groups, intermolecular forces, and isomerization. And I want to talk about some rules about stability. And I'm being told I'm recorded, which is good. So we should, hopefully, have a GA here helping me out. Samra, are you here?
Hello.
Okay, you are. Awesome. So it's going to be keeping an eye on, I'll turn on my video too, so she's not the only one with the video on. So Samra's going to be keeping an eye on the chat, helping us out and interrupting me when something really interesting comes on. You have access to the chat, right, Samra?
Yep, I do have.
Sweet.
Thank you.
Okay, awesome. So once I get going on questions, she's going to be your guide. She's also going to be helping me construct the exam, the assessments. She doesn't know this yet. I'm telling her in real time what's happening to her. And so if you bribe her really nicely, she might not tell you what's on them. But I don't know what she accepts. Yeah, I will post this new schedule. I just changed it like 30 seconds ago. How long will I take these assignments to take from start to finish? For the student who's been keeping up with the material, 20 minutes, 15 minutes. If you're not sure, I wouldn't leave it till 11:45 on Saturday night. That sounds like a really bad idea. Yes. The assignment will be on Blackboard. Is the assignment based on chapters 1, 2, 5, 6, or 1 and 2? It is based on 1 and 2 because we haven't gotten to 5 and 6, and holy shit, we're not covering all 5 and 6 this week. Whatever, I'm not going to ask any questions on stuff we haven't covered by the end of class today. Like that's on there. And what we've really covered is this stuff here. So chapters 1 and 2. Okay, opening the floor to if there's any questions. I got some questions by email that I can go to, but they're very, very specific, and I prefer to leave this open if there's more general questions that are available, and I'm not going to share my email. And I'm going to stop presenting, and I'm going to switch over to presenting the PowerPoint. People are saying probably 1 and 2. It is 1 and 2. Yeah. I just need to. You can watch me try in real time to see if I can actually. Oh God, I did not choose to do this the right way. I hate tablets. I hate tablets so much. Do we have a midterm date? Yes, and I'll post that. It's going to be the 23rd of October from noon to 4, and you have a 3-hour exam from noon to 4. So I guess if you choose not to start the exam till 1, that's fine. If you choose that you're done at 3, that's fine. If you choose that you're done at 1:30 and you start at noon, that's I don't care. You do what you like. Again, I will send out those details in an official thing. I'll probably just launch one announcement with everything in it. Yeah, it's on a Saturday because we need 3 hours and good freaking luck finding a 3-hour time slot when you guys don't all have other classes and things. Yeah, I'm not going to give you a, I'm sorry, I'm not giving you a 1-hour midterm, which is worth 30% of your grade. That sounds awful. Okay, any particular content questions? Okay, well, I guess what I'm going to do is I'm going to jump into, okay, Amanda wants to review LCAO diagrams. Amanda, did you send me an email about that? You did. Yeah, so Amanda has a good, add this device. Sorry, I'm just, again, getting myself sorted. So I can actually pull up the example you have. Can we do some naming questions? Sure. So what I can do is I can pull up what I want to do first is I just want to make sure I cover something what I think is really important. And so that's the rules on how to talk about charge stabilization because we've started discussing it. And that's what a lot of the lecture 6 that you might have been looking at is discussing. 2021. So I'll make sure I find that. Oh, no, that's not what chapter 6 discusses. Okay, we're fine. We don't really talk about that too much until later, so you're good. Not going to have to discuss that. Will name be on the assignment? No, I'm never going to ask you to name a compound because it's stupid. Except, well, not this assignment. There will be some stereochemistry naming. But let's share an example. I am sharing my screen. Fine. Let's talk about one of Amanda's questions. So she had a question from assignment X. I am just going to go open that and I will pull it open. Assignment X question 3A. So it asks to draw the LCAO diagram. So this is a good thing to do. Of this molecule. So again, whenever you're drawing one of these things, the first thing to do is draw out your carbon skeleton. Luckily, I didn't give you a condensed molecular formula, so you know what everything is attached to. If you can go through and try and assign hybridization now, or you can try and do that as you draw. If you are least bit confused about where hydrogens should be, because it's still new to you, this whole line angle drawing formula, you can put them in. So if what your first step on this is, okay, I'm going to switch the slideshow so I can, there we go, draw properly. So if your first step might be, I need to draw my hydrogens. I'm not 100% sure where the hydrogens are. I want to make sure they're there. So you would sketch in where the hydrogens are. There were 4 hydrogens missing from this structure. Notice that there's no hydrogen missing from that central carbon, even though it's only making 3 bonds. And that's because there's a negative written on there. And that means there must be a lone pair. Because any other way that you try and do that, you're not going to get a -1 formal charge. To get a -1 formal charge on carbon, you need to have a lone pair on carbon and not making a bond. Okay. Now, the second thing you want to do with all these is you want to try and keep your molecule as flat as possible because drawing in 3D is hard. So if we try and do that, I'm just starting over here. So this is carbon 1. I'm just starting with carbon 1 on the far side here. It's making a double bond. It's attached to 3 other atoms. It cannot be sp3, because if it was sp3, it couldn't make a double bond. It cannot be sp, because if it was sp, it could only be making 2 sigma bonds. But it's making 3 sigma bonds because it's attached to 3 carbons. So this one must be sp2. There's no choice for this guy. So this guy must be sp2. Similarly, this one here must be sp2. Again, there's no choice for it. It's making bonds to 3 atoms. And it's making a double bond. So it needs to have a p orbital to make that double bond, and it needs to have 3 hybridized orbitals to do that. And the only thing that satisfies that, if there's no option, it has to be sp2. This guy down here is attached to 2 atoms. And it's making 2 double bonds. So it's making 2 sigma bonds, and it's making 2 double bonds. So it needs to have 2 p orbitals to make the 2 double bonds. And if you're keeping 2 p orbitals for double bonds, that means you have to be sp hybridized. Again, there is no choice. Similarly, exactly the same argument, there is no choice for this guy. This carbon likewise has no choice. It is making 4 single bonds. It can't have a p orbital. It must be sp3. Now, the fluorines and the other carbon do have choices. The fluorine is making a single bond and it's got 3 lone pairs. And those lone pairs can be in p orbitals or they can be in hybridized spx orbitals, where x is 1, like 1, 2, or 3. So that fluorine can be sp3, sp2, sp. It could be. It is only one thing. So if we draw them out, that might help. Shit, I drew them out on the slide before I started trying to get a slideshow, so I can't erase them. But each of those fluorines is single bonded to the carbon. So what do you think the hybridization of the fluorines are? Got Alia with an sp3. Conflict. Madison with lower energy, sp3 because lower energy. I read that way, Madison, from you. A lot of sp3s. I agree with the sp3 crowd here. So again, sp3 is lower energy overall than sp2 or sp because those p orbitals are pretty high energy. So whenever possible, an atom will be sp3 unless it's got a reason to have a p orbital to make a double bond. And these ones don't, because the only thing they can make a double bond with is the carbon next to them, and that carbon is sp3. It has no p orbitals. It cannot make a double bond. So the fluorines can't make double bonds because there's nothing to make a double bond with. So they go, well, there's no reason for me to make a bond. I'm going to relax my electrons into the lowest energy orbital I can, and that's the sp3 orbital. So the fluorines are going to be sp3. Okay. How about this carbon? Now this carbon's got options. It could be sp3. There's nothing stopping us putting that lone pair in an sp3 orbital. After all, that's what these fluorines did, right? Each of these fluorines has 3 lone pairs. All those lone pairs are in sp3 orbitals. Nothing wrong with that. So lone pairs, fine. sp3, that's fine. So what do we think about the carbon? Do we think, I'm going to take Guntas there as the final response to the first answer. But what do we think about this carbon? Is it sp2 or sp3? It can't be sp, right? Because it's making bonds to 3 different atoms. So it needs at least 3 sigma bonds. Hamza's on team sp3. Madison's on sp3. Seeing a lot of sp3s. Christina. First of all, I want to give a shout out to everyone who is actually participating like this. You're getting more out of this, I think, because you're thinking about it. Jesse has sp3 because there's nothing to double bond with. Are we going to do, and Ali disagrees with that, saying, are we going to do resonance and move the lone pair, making it sp2? And, you know, we're really in the mix here. I'm going with sp2 because, again, sp3 is more stable unless there's somewhere to put that p orbital with. And there are, because both of those carbons have p orbitals. And so we can make partial double bonds with those, right? If you're next to a p orbital and you can make a p orbital, you're going to make a p orbital because you can delocalize your electrons. If it's sp3, that negative charge is stuck on that carbon. The carbon is left holding this really heavy weight on its own. It can't share the weight with anybody. The heavy weight is that pole negative charge. If it's sp2, it can share that negative charge with the adjacent carbons, and suddenly everyone's holding part of the negative. So it's going to be sp2 because of resonance. I think Noor did that in the shortest number of letters. sp2 resonance question mark. So let's just think about what that resonance looks like. So again, before we draw the LCAO, you might want to think about resonance, but also you might actually think about resonance while drawing the LCAO. So there's a few different orders you can do these things in, and none of them's the right way. Whichever one works for you is the right way. It's just everything needs to make sense with everything else when you're done. So if we're looking at the resonance structures of this thing, there is nothing stopping me drawing this molecule this way. Note, if you went through and assigned the hybridization of all those atoms, they'd stay the same. Everything would stay the same. This is a resonance structure. You're not changing the hybridization of the atoms. What's considered a stupid resonance structure? A stupid resonance structure is a structure that has too many charges, is generally it. So these both have 1 charge. They're both reasonable. But if I drew a resonance structure where, you know, I did that, so I had a resonance structure with 3 different charges, this one is a minor. Stupid is probably the wrong word. Probably the right word is a minor contributor to the resonance hybrid. It's not important. It as a percentage of the contribution to that overall structure. This one's really minor because we've got 3 charges there. And again, we haven't gotten to why we're going to rank different resonance structures different ways. We've gotten some questions about that. We're going to get to that once we start talking about everything all together, because we need more information before we can really rank them. But right now we can just sort of draw them and worry about the ranking later. So this one is 3 charges, bad. You want to use as few charges as possible. So all the ones I've called stupid have actually been because for one of 2 reasons. One is we've had more charges than we've needed. Sometimes you are going to have 3 charges and there's just nothing you can do about it. That's fine. But here we have more charges than we need. And the other ones that are stupid is when you invert the polarity. So if, for example, what I mean by that is, let's say you had an example like this. You can draw a resonance structure where you put the negative charge on the electronegative atom and the positive charge on the electropositive atom. That's wise. You could also draw a resonance structure where you put the electronegative, the negative charge on the electropositive atom and the positive charge on the electronegative atom. That is not wise or stupid. And the thing is that it's not that this doesn't exist, it's that it's a direct counteract to this, and this is far, far better. So this kind of swaps that out. Yeah. So Mohammed is really confused, and Alyssa, it makes sense. Yeah, yes. You can still draw it if it has 3 charges. You don't have to, because it's not going to participate in your resonance hybrid. It's not going to be a meaningful participant for the resonance hybrid. I'm just going to create some more space here. So we have this. Another resonance structure we can do from this one is we could delocalize those electrons down to here. So that's the second resonance. So we have sort of 3 good resonance structures here, which are going to participate in our resonance hybrid. There's no right one. They're all right. You wouldn't get marked wrong to add this, the third one here, Aurora. It's just not going to be necessary. You can draw it. It's not wrong to draw it. And if you're doing one arrow at a time, you have to draw that to make sense of things. It's never wrong to draw it. It's just not necessary to draw it. Do we need to know the bonding and anti-bonding orbital structure diagrams? I think you might need to be able to discuss them. Yeah. Yes, we're going to be talking about relative resonance because we need more things to discuss this. How many double bonds are in a red one? 3. There's a carbon in the middle here. Yeah, it's not completely clear. I'm sorry. There's one up here. There's one here. This carbon is making 2 double bonds. And what we're going to see is that we can describe all 3 of these molecules and the resonance hybrid using the same LCAO. So again, what does our resonance hybrid look like? This time I'm going to dot the lines because somebody caught me out on it last class and it was really good. So you draw the bonds that are always present. So the bonds that are present in all 3 of those, and you'll notice also in this one, is there's going to be a double bond down here. Damn it, I just turned into a triple bond. I did not mean to do that. Double bond down there, single bonds everywhere else, and then everything else is dotted. There's an overall -1 charge, and there's negative charges at 3 different places. Right now, it doesn't matter too much the route where you're putting those negative charges. Like the relative, sorry, not that, no, that matters a lot. The relative size of the negative charges doesn't matter right now because we haven't discussed that. I'm sorry. Where they are is very important, but the relative size is not important. Isn't that carbon with the two double bonds going from 2 sigma and 1 pi to 2 sigma and 2 pi? No, it always had 2 sigma orbitals. So this carbon here, I think is the one you're talking about, this carbon here. It still had 2 sigmas, one here, one here. It still has 2 sigmas, one here, and it still has 2 pi's. They were both over here, now one's here, one's here. So it still has 2 pi's. So Madison, Carolyn asked, should we show one transfer electron of each resonance structure? Can we make 2 changes in 1 step? You can make 2 changes in 1 step. I wanted to show, when we first done this, I wanted to make sure I was going really slow. We're still really early, but you can make 2 in 1 step. That's okay. You can actually make 100 in 1 step if you like, if they're all flowing. Yes. And there's a carbon in the middle, and I've drawn it like that. Another way to draw this, and I'm sorry, because of course there's another way to draw this, is this is the same. That's not a double bond, that's an equal sign. I just put a dot in the middle, and the dot means a carbon atom because writing a C is too long, and so we need to draw a dot. So the second way is actually the preferred way. Sorry, it is. And so you're going to run into that, I think, in the textbook and in other sources. No, your assessments are going to be easier. None of your assessments are going to be quite this nasty. Your midterm and final, possibly. This one isn't too bad, but I would say that in general, the assignment questions are harder than any questions you will see on any midterm or final. The assignment questions are there to mess with your minds. The midterm and final are not there to mess with your minds. The midterm and final are there to, do you know what you're doing? Dotted lines represent partial double bonds. So in some cases there's a double bond there, and in some cases there isn't. Okay. What we're going to do now is, again, drawing the LCAO here. We now have all the hybridization. So carbon 1 up there in the top right-hand corner is inexplicitly going to switch to maroon because I just can't be bothered to fix that. So we have the orbitals attached to the hydrogen. It's attached to another carbon, carbon 2, to an sp2. It's attached to a hydrogen. I'm going to run out of space, aren't I? Actually, I might be okay. I might have cleverly organized everything to make this work. I'm just going to have to elongate some of these bonds. So what I'm doing is I'm drawing in the sigma bonds first. This is always a good idea. Just draw in all your sigma bonds. Why? Because they give you the skeleton to make sure all your atoms are in the right place. You don't forget any atoms. It's really easy to get pretty proud of yourself when you've sketched in your pi bonds and then realize you forgot all your atoms. I'm don't know what I drew in the answer key. I could have drawn in, because these aren't attached to anything else, I'm just going to indicate these guys are sp3, and I'm not going to try and draw in the orbitals, but I think I did in the answer key. So you can check that. If what I could say is don't bother drawing in the orbitals for lone pairs on terminal atoms that aren't doing anything interesting. And then you could do this, but I probably will ask you to do it. The reason I'm not doing it here is because I literally don't have space because I'm trying to put all this on one slide. you're going to have paper and you can take as much space as you like. So I've drawn in the core of this whole thing. Now I'm going to put in my p orbitals. The easiest p orbital to draw, because everything else is in the plane, that means that the p orbital for this guy has to be coming directly out and going directly back into the plane away from me. So this carbon here is this central carbon here. Then for each of the other guys, they're to be able to participate with this, be able to make that double bond with resonance, the p orbitals need to be aligned. If they're not aligned, there's no way to do resonance. There's no way to make a bond. So both of these carbons need to have their orbitals in alignment with the other guy. Everything needs to be parallel. It's not parallel, no resonance. So every one of those is directly coming out towards me. Now we covered those guys. Those were sp2. All those guys were sp2. They all have one p orbital. Sweet, numbers check out. This guy also has a p orbital that is, you know, perpendicular to the plane of the page. So does this guy, because they're making a bond. It's just these two guys down here also have another p orbital, which is in the plane of the page. Okay, so I think the thing I want to discuss, so these are sp hybridized. That's what sp hybridized look like. They've got two p orbitals crosswise, and then the sp orbital kind of runs like this. Like everything tries to get as far away from everything else as possible. So everything's at 90 degrees to everything else. There are 5 carbons because there are 5 carbons. Mohammed asked why there are 5 carbons. 1, 2, 3, 4, 5 carbons. How do I know when an orbital is coming in out of the page? I'm trying to sort of shade the outline of this to sort of show that it's coming towards me, it's getting thicker. And I'm dotting the outline of this one saying it's going back and away from me. That's how I know. If you're really good at perspective, you could do it a different way, but this is faster than any kind of perspective drawing. The reason we're going to do this is we're going to start talking about stereochemistry in the next bit. This is going to be analogous to what we're going to be using there in terms of demonstrating going into the page and coming out of the page. So we didn't specify which ones were coming in and out. Would it be wrong? No, but they need to be 3-dimensional. Like they need to be, they can't all be flat because it's not flat. It's in 3D. Okay, Julia asked, do we show where they would bond or leave it blank to cover resonance? So it depends how I asked the question. So the way I asked this question was, draw the LCAO of the following molecules, assign hybridization of all non-H atoms, label all bonds, label all non-hydrogen orbitals, draw the resonance hybrid. So I have to draw the bonds if I'm saying label all bonds. And so what I would do, draw the resonance structure I gave you. Like that's where you're going to draw the bonds. You can choose any of the other ones. It would be right. You could choose any of the 3 down here. It would be perfectly right. But just in case you did it wrong, draw the one I started with, and it also acts as an extra check to make sure that you translated that structure into this. Because if suddenly there's a double bond in the thing I gave you and you can't draw a double bond now, you've done something wrong. So if we do that, and we answered all 5 of my questions, we've already drawn the LCAO, we've assigned the hybridization, we haven't labeled the bonds, and we haven't labeled the orbitals. So if I do that and I label this, I have 2 ways to label this. They are equal. I could write pi and sort of draw arrows pointing to it from both of them. That's fine. I could write 1/2 pi right next to it, 1/2 pi. I don't know what just happened to my pen there. 1/2 pi. This is a little bit neater because you have maybe fewer arrows. Those are all the pi bonds. There are 3 pi bonds in my starter material. I have now labeled 3 pi bonds. I'm pi'd out. So now I need to label a sigma. Any place where 2 atoms join is a sigma, so you just go happily around sticking sigmas everywhere. Kind of mindlessly sigmaing it up. And then label all non-hydrogen orbitals. So this is a p orbital. Let's change color again. This is a p orbital. 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 P, p, p. This is sp, 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 because it's attached to this carbon, right? So it's still sp. This is sp2. So is this. These are all sp3. These are both sp2. These are both sp2. These are always going to be messy diagrams. There is no way to make them super tidy. Oh, I've already labeled that one. So I've labeled all the non-hydrogen atom orbitals. I have labeled all the bonds. Everything's labeled. Now you're going to probably be able to space this out over a much bigger piece of paper than I've just spaced it out over. So it's going to be a little bit clearer for you guys than me. You can use different colors if you like different colors, Hamza. You can use the same color. You can write in pencil if you like, because you're going to submit your questions by emailing them to us. So we have a permanent record. So if you like pencil, this is the first. This is like the 1 year you can write an exam in pencil. You can write it in chalk or charcoal or anything you like. I don't care, because you're submitting me pictures. Wait, so why is the lone pair in a p orbital? I remember doing a question a bit ago, and the lone pairs were in a hybridized orbital. Right, so the lone pair of the carbon is in a p orbital. That's what we're talking about there, right? Alan? Yeah, you can do it on an iPad. If you prefer to answer your key questions on an iPad, you can do it on an iPad. You're submitting images, you can draw it however you like. I think paper, iPads are maybe better than this. This is a Surface. These are shit. Yes, you can use OneNote. No, Aurora, you cannot use OneNote and send a link. You can use OneNote, convert it to a PDF, and send me the PDF, because a OneNote can be edited after the time. So you can't. You have to send me a PDF or an image, something that can't be modified. So no links. Alan, so why is lone pair in a p orbital? I remember the question a bit ago. So you're talking about this lone pair, right? Just want to confirm we're on the same page. Yeah, okay. So it's in a p orbital because it can do resonance. We need to use this electron, this lone pair, to make the double bond with the adjacent carbons. And so if it was in an sp3 orbital, it would not be able to do resonance, and that would be less stable. Resonance is always good. I think in here I said label all non-hydrogen orbitals, Christian, so you got away from that because I'll give you that. You don't need to. I didn't ask for it. I will never ask for it. It's kind of annoying. I might say draw in any lone pairs that are seeing in orbitals. That's okay. There's nothing wrong with labeling more stuff. If you do more than I ask you to, all that can happen is you can get it wrong and lose marks. But if you do it right, there's no marks lost. And if you're not complete, that's fine. And yeah, you can carve it on a stone tablet and submit the stone tablet. You can submit the stone tablet by mail. You'd have to do the exam really fast, or you can take pictures of your stone tablet. But I think carving is a very slow words per minute, so I wouldn't recommend carving on stone tablets. I don't know if that helped you, Alan. Okay. Great. I'm useful. No hydrogens are ever hybridized. Hydrogens are always S. How does this diagram represent all resonance structures? Because I can suddenly, like, let's say I don't want the double bond between these guys. I could draw a double bond between these guys here equally. And then all I need to do is move the electrons over here. So I don't need to change any hybrids. I don't change any orbitals. I just change which p orbitals are doing that. But what I've just drawn now is this guy here. And I can draw these equally by just rearranging where the double bond, which adjacent p orbitals are interacting. No naming on the assignment. You don't need to write an S because I didn't ask you to. Because I said don't worry about the hydrogens. Does it matter where we connect? No, as long as you do it in the right way. You can draw any of the resonance structures. I just said it's always easiest to draw the one I give you because then you can double check your work. But now the one I've drawn is this one here. And that would be full marks. They're both full marks, so the same thing. So pick your favorite, if you have a favorite, which would be a bit weird. Okay. Any questions from anyone about intermolecular forces? Hydrogen bonds, van der Waals interactions, London dispersion interactions? I know that's review for most of you, I think. I think you've seen that stuff before. Okay. Any questions about functional groups? We're going to get to the Zen-E stuff a little bit later. It is confusing. So you're right. Yeah, up to lecture 6. We just do an example so you know what to ask. So I know what to ask. Sure, let's do an example. So let's say I ask a question. Which has a higher boiling point and why? Intermolecular forces are not, intermolecular forces are not important when drawing a resonance structure. Because resonance structures are always within a molecule, and intermolecular forces are always outside of the molecule. So intermolecular forces are intermolecular between two molecules, but when we're drawing the resonance forces, we're drawing one molecule. So its intermolecular forces are irrelevant. Okay, so we got A and we've got B. So these have, so there are many things that go into a boiling point, right? Probably the most important thing that plays into the boiling point is molecular weight. Heavy molecules have higher boiling points in general. The next thing that goes into it is, well, a boiling point, right, is the amount of energy, is the temperature, which is just energy, is the energy at which things go from liquid to gas. So if you need a higher boiling point, it means you need more energy to go from liquid to gas. And so what that means for a pure substance is you need more energy to break up the intermolecular forces, because the intermolecular forces is what keeps it a liquid. In a gas, you don't have strong intermolecular forces because it's a freaking gas and the molecules are floating around everywhere, right? And in a solid, you have really strong intermolecular forces because everything's packed in real tight. A liquid's kind of an intermediate, wishy-washy state, literally washy. So if I don't laugh at my own jokes, even when they're really, really bad, no one else is going to laugh at them. So the question then is, which of these has the higher boiling point and why? So you need to think about what intermolecular forces are going to play a role here, because they have the same molecular weight. I'm sure there's some way I can like do polls and stuff on Teams, but it'd probably take a long time to set them up, and I don't think about that. B, because of hydrogen bonding coming from Madison. ISIte agrees. Selwyn has a question mark saying hydrogen bonding. That the B's are heavy. Do we have anyone for A? And if A, what would be the argument? It's all B, and you're all right. So in A, what we have is we have a strong dipole moment, right? Because A has a resonance structure. It's a damn good resonance structure. Actually, that's exactly what we're doing, Alan, because this is an alcohol and a ketone. So A has a resonance structure. It's a good resonance structure. It's got a strong dipole moment. If we draw in a dipole moment of this, so we draw a little cross down here saying, hey, that's the positive side, and the arrow points towards where the electrons are, because electrons go places and charges don't. So we have a strong dipole moment here. And what's going to happen, of course, is acetone, which is that molecule, is going to kind of stack itself so that the dipoles all align. You know, so one partially negative section can interact with a partially positive section through a dipole-dipole interaction. Whereas B has strong hydrogen bonding. A hydrogen bond is like is basically an extreme version of a dipole-dipole interaction. There's nothing magical about a hydrogen bond. It's just a really freaking polarized bond. So in a hydrogen bond, and a hydrogen bond can happen anytime you have a heteroatom attached to hydrogen. So a heteroatom is anything that's not carbon, because carbon and hydrogen are more or less neutral. Their electronegativity is pretty similar. The bond's not really polarized very much. Any other atom polarizes it more. Now, I will have colleagues who will disagree with me and say that's not true, John. If it's a third or fourth row element, it's not a true hydrogen bond or something else going on. And I say you're picking details. It acts like a hydrogen bond. It quacks like a dihydrogen bond. It's a freaking hydrogen bond. It's a polarized bond. It acts like that. That's all I care about. So I'm defining a hydrogen bond. This is not the IUPAC definition, but it works better as any bond where hydrogen is attached to a heteroatom can form a hydrogen bond. And so you would have an interaction with an adjacent molecule of this, where the big delta minus on the oxygen and the big delta plus on the hydrogen interact with the big delta minus and big delta plus on the adjacent ones. And you'll have an interaction between that oxygen and that hydrogen. That's because heteroatom hydrogen bonds are pretty weak. So these are this is the same thing as that. It's a dipole-dipole interaction. It's just a special subclass of dipole-dipole interactions, which tend to be quite a bit stronger. Does double bond have anything to do with it? No. The double bond just keeps the molecular weights of the two molecules the same. It has nothing to do with the strength of the intermolecular interactions. So this is why Alan's question, why alcohols have higher boiling points than ketones of the same molecular weight. or similar, very similar molecular weights, and that's because alcohols can hydrogen bond, ketones can't. Now, be very careful because a hydrogen bond needs two components. It needs a hydrogen bond donor and it needs a hydrogen bond acceptor. So if I put a mixture of acetone and the alcohol together, acetone is a hydrogen bond acceptor. It's accepting the hydrogen. And the alcohol is the hydrogen bond donor. It is donating the hydrogen. And I really hate this terminology because normally when we are going to talk about donors and giving and that kind of thing, we're going to be talking about moving electrons. And we're not talking about moving electrons here. It's kind of the opposite. The hydrogen bond acceptor is giving up electrons, but it's accepting the hydrogen. And this is because chemistry hasn't been named in sequence when we understand what's going on. These terminology predate us understanding where electrons are. Yeah, if you have to leave, yeah, like this is the end. So this would be an example of a question that I would give. Any other questions for now about functional groups?
Will you ask anything about bond angles and special cases such as ammonia?
Well, ammonia is not a, well, you know what? Yes, it's not precisely 109.5 degrees, but it's 109.5 degrees. Who cares? So I might ask things about bond angles, but it'll basically be say, hey, is this 109.5, 120, or 180?
Okay, so there won't be like 107s.
No, because it doesn't matter.
Okay.
It just doesn't matter. Can I do a different example, like a boiling point question? Would they be more complex than this? Not really. Okay. What functional groups are you feeling, Elisa? Oh, I have no clue. Putting me on the spot here. What other kinds of questions could I ask about this? I might ask you to rank the boiling points of things. I might ask you to rank the strengths of expected intermolecular interactions between molecules. I'm not going to ask you about melting points because melting points are a little weird because you get this weird thing going on with the length of the carbon chain, and I don't want to get into that because it's not important. So maybe another type of question I could ask you would be, okay, it's actually basically the same question, but it's just phrased differently. This is not a zebra or a horse. I don't know why I said zebra. Nobody thinks that this looks like it, but there's like a tail and a head and like two legs and shit. 6, 7. So it's 7. So if I could ask, which of these has the higher boiling point? So that one's on B, having a higher boiling point. The second one, okay, yeah, you know what? You guys know what you're talking about. Well, Joshua, they're both heptanes. Just one's linear, one's not. Crystal got it there. That's better than more spread out. I like Crystal's answer better, so a greater surface area. A has stuff more compressed. It's kind of more, you know, it's a sphere, more or less. Whereas B is a long thing, and long things have more opportunities to interact with the next long thing. So you have better interactions.
I don't think the first thing is a heptane, is it?
It's got 7 carbons.
1, 2,
Yeah,
3, 4, 5. That's the longest chain I see.
Yeah, you would write it as a pentane, like you would name it as a pentane. So you would name this as 2,3-dimethylpentane. But if you're gonna if I'm selling you a bottle of this and I call it heptanes, it could contain that because it's got 7 carbons. So it's a branched heptane, but you would name it as a pentane. So I'm sorry. Yes, because it acts much more like a it's going to have boiling points in the heptane region, not the pentane region. So you can buy I buy things like, it's called hexanes, and it's not because it's got a 6-membered ring long chain and lots of stuff off of it. It's all the atoms and all the molecules in there are 6 carbons long. It's just some are linear, some are branched. Like some might be a butane that's doubly branched or something, because it's kind of a cut of distillation. So we would classify both of these as heptanes, even though the name for the first one is a pentane, but it's got 7 carbons. And that, you know what, forget I said anything about this. It's on the record. But if you're going to name it, you would name it a pentane. You're absolutely right when you're saying I don't think it's a heptane. It still is a heptane, but you would call it a pentane. Anyways, the longer chain, higher surface area. So higher boiling point. Okay, I saw somebody say amide. So let's compare an amide versus a similar ester. So which of these would have a higher boiling point? Let's throw in a few more just for shits and giggles. We'll toss in the diketone, and we'll put in a diether. So now there's 4. So those of you on team A, that was A versus B. Any of you want to revisit your answer? Or do you still think it's A even with all 4 of these? Yeah, I'm still going with A. A is number 1. Okay, what do we think about number 2? Yeah, it's nitrogen attached to a hydrogen. Sorry, yes. Or maybe number 4. Which one's going to be the lightest? That might be easiest to start with. The lowest boiling point. And it's for B for being the lowest boiling point. D.
Yep.
BD, BD, B. Do we have another D? Okay, now you're just messing with the chat. Definitely is going to be D. Why? Because it has the weakest dipoles. This has an ester. An ester has a pretty decent dipole. You got that carbonyl, you've got resonance, you've got decent charge separation. You can put an O- and a C+. You can't do that with an ether. Everything in this ether is sp3. The boiling point of this guy is probably actually, 30 degrees below anything else there. And then B and C, I wouldn't ask you this question because it's not completely clear. C is going to win as being a higher boiling point, and it's not so much because of anything to do with it, it's because it's higher molecular weight. If you count the number of things in there, there's 4 carbons on C versus 3 carbons on B. The polarity of them is actually pretty similar because C is going to arrange itself like this, and the dipole moments of both of those ketones are going to cancel each other out. And yeah, it's going to help it pack a little bit better, but the effect is greater on the ester. But just C is bigger. It's got an extra carbon.
What about the symmetry of B? Wouldn't that make it a pretty close contender?
When the symmetry of B?
Yeah.
What symmetry?
Well, exactly. There's no symmetry.
Okay, the lack of symmetry of B.
Yes, there we go.
Does that make it more? That makes it where you're saying that's good or bad for boiling point, like higher or lower?
That's of course better for boiling point. It means that there's like poles at either sides of the molecule. Stuff.
I like that. Yeah, so you have a more defined dipole, whereas these guys kind of cancel each other out.
Yeah.
So this is going to be high. That does help with this, but it's bigger. And it's hard to come out. And I've drawn it this way, and we haven't gotten to this quite yet, but there's nothing stopping those bonds rotating to give us that, in which case the dipole is predefined.
Okay.
So C is bigger, is I'm going to say the big thing there. So size and functional group matters. You know, because if I took D, if I had these same examples, except I added in an E, and it was this. You know, that nothing really polar on that, but it's just so much bigger than A that it would be a higher boiling point. There's just so much more mass. There's so many more van der Waals interactions it can participate in. So we're sitting at, is that trans and cis then? Right now that is neither trans nor cis. None of these are trans or cis. Madison, I think the thought process should be what we just went through. So trying to find, okay, are they all about the same molecular weight? Do I need to take that into account? Yeah, they're all about the same. There's a little bit of difference there. Then start looking at functional groups and then try and find time breakers. I would not give you B versus C. That is an unfair question. I will make that clearer. Ketones always have a higher boiling point than ethers at similar molecular weights. Molecular weight trumps other things in general, but you know, C is a little bit heavier than A, and A is still going to be a higher boiling point because of the hydrogen bond. So I think this is where we're getting into part of what makes this really challenging is I can't say there's any hard and fast rules. It's you have to balance things against one another. I'm going to try not to ask too many edge cases, but the problem, of course, is reality is full of edge cases. Thanks for looking that up, Sarah. So yes, C is actually higher, which is good. It goes A, C, B, D for boiling point. What is a ketone again? So it's in a ketone is a functional group where you have a double bond between a carbon and an oxygen, and the carbon is attached to 2 carbons. That is a ketone. An aldehyde is when you have a double bond between a carbon and an oxygen, and one of the carbons is attached to a hydrogen, so that's an aldehyde. An ester, an amide, is when you have a double bond between a carbon and an oxygen, and the carbon is attached to a nitrogen. And an ester is when you have a double bond between a carbon and an oxygen, and the carbon is attached to an oxygen, which is attached to a carbon. If it's attached to an H, a hydrogen, that's an acid. So these are all functional groups of carbonyls, and a carbonyl is the name of this. It's a carbon double bonded to an oxygen as a carbonyl. So Ketones, aldehydes, esters, amides all have carbonyls in them. It's kind of like a building block of a functional group. All assessments are open book. Because if I don't say they're open book, then some people would actually not use open book and other people would use open book, and that's not fair. What constitutes a stronger dipole? Stronger charge separation.
Oh, Professor Trent,
Yeah.
could we meet up after this lecture to try and figure out the whole text box thing? Because
Yeah, that's a major problem. Yes. If anyone else is having trouble with that, stick around. Otherwise, I think we're done because we're 16 minutes after time.
there's like the entire class, and then it's just